Hi everyone, my name is Saad and I'm doing PhD at Koç University, Istanbul, Turkey. I'm working on the inorganic quantum dots for the antibacterial application. And today I'm going to present with you type 2 benzyl structure indium phosphide zinc oxide covalent quantum dots for the antibacterial application. So let's start with the introduction of the quantum dots. What is quantum dot? Quantum dots are semiconductor nanomaterial and its size usually range from 2 to 10 nanometer. One of the most significant property of these quantum dot is quantum confinement effect. Now, what is quantum confinement effect? Suppose we have a bulk semiconductor. In a bulk semiconductor, we have a continuous energy level, and if we decrease the size of this bulk semiconductors to the molecular level, we can see here that the continuous energy level become discrete. And due to these discrete energy level, we can easily tune the size of the quantum dot. For example, if you see to this picture, these are the indium phosphide and zinc sulfide covalent quantum dot, and I have synthesized these quantum dot by controlling the size of the quantum dot. Here we can see that we can synthesize all the green, yellow, and red and deep red emission quantum dot. Basically, we have two types of quantum dot. One is type 1 quantum dot, and the other one is type 2 quantum dot. And type 1 quantum dot, both the electron and hole are confined in the core of the quantum dot due to the high band gap of the shell of the material. And due to this confinement, both electron and hole recombination rate is high, and they emit most of the energy as a photoluminescence emissions. And due to which these quantum dots are mostly used for the LED application or bioimaging application. In type 2 quantum dot, one of the electron or hole uh, also dissociate to the shell, and due to which we have rate of recombination of electron and hole, and they have better dissociations, and due to which they can easily move to the surface of the quantum dot, and at the surface of the quantum dot they can easily perform the redox reactions, and these types of reactions are good for the photocatalysis application. So here I'm going to discuss with you type 2 quantum dots, but how we can use these quantum dots for the RO generation and antibacterial activity. Suppose we have a semiconductor nanomaterial, and in which absorbed light energy greater than its band gap, a photoexcitation of electron and hole occur, and these charges moves to the surface of the material, and at the surface of the materials they perform the redox reaction. So, for example, the electron reduce the oxygens, okay, reduce the oxygens to the superoxide radical, while the whole oxidize the waters to the superoxide radicals. These species are called reactor oxygen species, and they are attack on the bacteria, and they degrade the cell membrane and other components of the bacteria, and due to which the bacteria cannot survive. So we will also use this mechanisms, ROS-based mechanisms, for the antibacterial activity using our quantum dots. Previous state of art for the quantum dots. Basically, we have a lot of studies have been conducted for the inorganic quantum dot, but all those quantum dots are cadmium based, and we cannot use cadmium for the biological applications, and due to which we have proposed a cadmium-free non-toxic quantum dots, a solution for the antibacterial activity. So I'm going to share with you like type 2 quantum dot. Basically, we use for the first time this type 2 benzyl structure, and also cadmium-free quantum dots for the antibacterial application. So let's start with the synthesis of these type 2 quantum dot. We synthesize indium phosphide quantum dot by hot injection method. In hot injection method, we dissolve one of our components like indium, and then we inject the other precursors, which is phosphorus, and due to this injection, so the sudden nucleation of the crystals occurs. And for the zinc oxide shell growth, we use the thermal decomposition of zinc acetate acetonate into hydride. After the synthesis of these quantum dot, we have confirmed the growth of zinc oxide shell by the TM analysis, and here we can see that the size of the core quantum dot is 3.05 nanometer, and after the growth of one zinc oxide shell, the size increases to 3.54 nanometer, and after the growth of three zinc oxide shell, the size increases to 6.25 nanometer. We also perform the ETBAS analysis to confirm the zinc oxide shell growth, and The Zn2P spectrum indicates that zinc has bonded to the oxygens, and it's confirmed as successful growth of zinc acyl on top of indium phosphide core quantum dot. We performed the quantum mechanical calculations for these quantum dots with the help of Professor Mehmet Sahi. He performed the quantum mechanical calculation. This figure shows the quantum mechanical calculation of indium phosphide core quantum dot, and this is the radius of the quantum dot. We also saw in previous slides that indium phosphide core quantum dot has a size of around 3 nanometer. So its radius is 1.5 nanometer. And we can see here is that at this range, both the electron and holes are confined in the core of the quantum dot. This red line indicates the wave function of electron, while this line represents the wave function of the hole. Sorry, this line represents the wave function of the electron, and this line represents the wave function of the hole. And after the growth of zinc oxide shell, we can see that still the hole is confined in the core of the quantum dot, but ZIL is but electron wave function is also exceeding to the zinc oxide shell. It means that after the growth of zinc oxide shell, we can easily dissociate to the electron to the zinc oxide shell, and we can easily decrease the rate of recombination of this electron in hole, and we can have better options for the reactive oxygen species generation. Uh, Ligan exchange process. When we synthesize these quantum dots, it was oleolamine kept, and due to this oleolamine kept, they were only soluble in the non-polar solvents such as hexane or V. And we cannot use these quantum dots for biological applications because for the biological applications, the quantum dot should be soluble in the water. For this purposes, we replace the oleolamine kept ligands with the sulfite ligand. Here, we dissolve the sulfide precursor in methyl formamide, which is high polar solvent, and quantum dot dissolved in the hexane. After the stirring, we can see here that the quantum dot has been transferred from the hexanes to the N-methyl formamide, and it shows the successful ligand exchange process. And we confirm that polyamine ligand is successfully replaced with sulfide ligand. Further, we perform the optical characterization, and here this figure shows the PL emission of the quantum dots. We can see here is that after the zinc oxide shell coat, there is a red shift, and this red shift is due to the uh, dissociation of the electrons to the zinc oxide shell. And this redshift further increases after the sulfide ligand exchange. And here we can see that after the sulfide ligand exchange, the photoluminescence quantum will also decreases. And it is due to that excess square space formation of the ligand exchange, and due to which we observe the redshift. And also we observe that P photoluminescence quantum will decreases. Further, we also detected the ROS species. Basically, we have three types of ROS species. One is superoxide radical, the other one is hydroxide radicals, and the third one is thin oxygen. These reactor oxygens already we discussed that attack on the bacteria and kill the bacteria, but we don't know which reactor oxygen species we are generating. So first, we perform the general ROS study, which is DCF. DCF is a sensor molecules which shows the when reactive oxygen species react with this DCF, it emit emissions at 525 nanometers, and we can detect that either ROS is generating or not. So we perform the ROS generations for different indium phosphide core quantum dot as well, and one zinc oxide shell, two zinc oxide shell, and three zinc oxide shell grown on the top of the indium phosphide core quantum dot, and we observe that one zinc oxide shell shows the highest ROS species. But I already discussed that this DCF is sensitive to the all ROS species, and we don't know which ROS species we are generating. So further, we perform the specific ROS reactive species. For the singlet superoxide radical, we use XTT assay, and when XTT react with superoxide radical, it generate XTT parmesan, which show absorbance at 475 nanometer. And here we can see that at dark, when there is no light, there is no ROS generation. So there is no absorbance at the 470 nanometer. And when we radiate it with the light, so there is a generation of superexcited radicals, and this superexcited radical react with the SPT and it generates SPT parmesan, which should absorb at 470 millimeter. Here we can see that SPT parmesan generation increases with the time. It means that we are generating superexcited radicals. Further, we also try to detect to confirm other species, which is singlet oxygen. For the singlet oxygen, we use ABDA sensor molecule. And when singlet oxygen react with this ABDA sensor molecules, the photo bleaching of this sensor molecule occur. And here we can see that at these two characteristic peaks, there is no decrease in the absorbance. It means that we are not generating any singlet oxygens for this counterparts. Then we perform the whole scavenger studies to further confirm other ROS species, and we use isopropanol for the detection of hydroxyl radicals. Basically, we use methyl violet degradation dye, and here with no scavenger, we can see that almost about 90% of the dye degraded in 30 minutes. But when we introduced IPA, isopropanol, so the degradation rate decreases from 90 to 60, 70%. That means that we have also small amount of hydroxyl radical generation. And when we introduce BQ, it almost degradation rate decreases to around 30%. So that means it shows that basically we are mostly generating superoxide radical, but we are also generating some amount of hydroxyl. And finally, we propose the reaction ROS generation mechanisms for this type 2 indium phosphide ring oxide quantum dot. Here we say that when we shine the light, it generates electronic hole. This electron react with oxygen and generate the superoxide radical. And this further superoxide radicals reacts and it generates the hydroxyl radical. So we provided these quantum dots to our Push University Hospital here to a group of Professor Kushan Jan. She is a professor and she works on the mostly this antibacterial activity. So first they perform the survivability, cytotoxicity of these quantum dots, and they used they checked the Viro E6 cells for the cytotoxicity, and here we can see that at they checked as zero, which is no concentration, and highest 125 micromolar concentration of the quantum dot. Here we can see in the dot that there is no cytotoxicity. And when they shine with the light, green light, which is 530 millimeter at an intensity of 5 milliwatt per centimeter square, still we can see here that there is no cell cytotoxicity. It means that the cell viability remains about at 90% quantum concentration of 0 to 1.5 micromolar. That means that the quantum dots are not toxic in the dark as well as under the light condition. So further, we used antibacterial activity. We measure the antibacterial activity of these quantum dots under the same light exposure, 530 millimeter at intensity of 5 milliwatt, and we used Pseudomonas aeruginosa. This is gram-negative bacteria, and here we can see that after the light at the dark there is no antibacterial activity, but under the exposure of this light, we can see here that up to 75 macromolars, almost a 5-log reduction of the bacteria occur, which is 99.99% of the bacteria. It means that under the light condition, it kills 99.99% of the free aeruginosa bacteria. While for the gram-positive bacteria, which we use Enterococcus bacillus, this is a gram-positive bacteria, and we see here that there is no antibacterial activity even under dark and under light conditions. So, a conclusion, I will say that quantum simulation and structure and optical analysis confirm the successful synthesis of type 2 indium phosphide ring oxide quantum dot. And we type 2 indium phosphide quantum dot generate multiple ROS species, which is hydroxyl radical and superoxide radical. While we also test these type 1 quantum dots, which only produce superoxide radical, I did not show in this the results of this slide in this presentation. And we also observed that these quantum dots show the efficient antibacterial activity, almost 5-log reduction of the algenisa, and emission under low intense green light, which is 5 kilowatt per centimeter square. And we also observed that this quantum dot shows the excellence biocompatibility, almost 90%, about the 90% of the cell variability across 0 to 1.5 micromolar under both dark and light conditions. So, thank you to all, to everyone, and I will also acknowledge my supervisors and some of my other collaborators. And uh, I'm also very thankful to the Mary Curie because this project was supported by the Mary Curie. So thank you everyone. And so if you have any question, you can ask to Dr. Valankar. Maybe I can also provide you by email or some messages. Okay, thank you and have a good day.